Ionization energy. There's a close correlation between electron configuration, which is a microscopic property, and chemical behavior, which is a macroscopic property. The chemical properties of any atom are determined by the configuration of the atom's valence electrons. Stability of the outermost electrons is reflected directly in the atom's ionization energies. Ionization energy, or IE, is the minimum energy in kilojoules per mole required to remove an electron from a gaseous atom in its ground state. The amount of energy in kilojoules needed to strip 1 mole of electrons from 1 mole of gaseous atoms is another way of stating the definition. We use gaseous atoms because they're not influenced by intermolecular forces. Gaseous atoms are very far apart, so they're not interacting with any surrounding particles. The magnitude, or the value, the number of the ionization energy, is the measure of how tightly the electron is held to the atom. So the higher the ionization energy means the electron is harder to remove. There's a stronger attraction to the nucleus. First ionization energy refers to the energy needed to remove the first valence electron. Second ionization energy refers to the energy needed to remove the second electron. Third ionization energy is the energy needed to remove the third electron, and so on and so forth. So you can continue to remove electrons. As you continue to remove electrons, though, it should be getting harder to remove them because of the increased effective charge attraction of the nucleus. Valence electrons are relatively easy to remove from the atom compared to the core electrons. Thus, there's a large jump in ionization energy between the last valence electron and the first core electron. So if we look at our data for lithium, lithium has 1 valence electron, and then we see a high jump when we remove the second electron. That indicates to me that the second electron is a core electron. For beryllium, the largest jump happens between the second and third ionization energies. So that tells me there's 2 valence electrons and 2 core electrons. If we jump down to carbon, the largest jump occurs between 4 and 5. So there's 4 valence electrons, and then the 5th and 6th electrons would be core electrons. So we can use this data without knowing the element. We can use the data to determine the number of valence electrons. When an electron is removed from an atom, the repulsion among the remaining electrons decreases. More energy is needed to remove another electron because it's held tightly by the positively charged ion. So the nucleus, which is positive, is going to attract those fewer electrons more than before. So the first ionization energy is less than the second, which is less than the third, and so on and so forth. So each time we remove an electron, the ionization energy should be increasing. Ionization is always an endothermic process. So energy is absorbed by our atoms or ions, and the ionization process has a positive value. Apart from small irregularities, the first ionization energy in a period, so as you move from left to right, increases with atomic number. This is because there's an increase of the effective nuclear charge. The larger the nuclear charge, the more protons you have, the electron is held tighter to the nucleus. For a given group, as you go from top to bottom, the ionization energy tends to decrease because you're increasing your N value, or the energy levels are increasing. So the electron is actually farther from the nucleus, so there's a weaker attraction. One exception occurs between groups 2A and 3A, the elements in the same period. So group 3A have lower first ionization energies than 2A. So if we go back to our graph, we see a blip occurring between, here it is, between 2 and 3. Oh, that's the D block. So why is 3A lower than 2A? Well, that's because 3A has a single electron in the p sublevel, whereas 2A has a full 2s, or S2. So the inner electrons or the single electron in the p orbital of 3a is shielded more, so there it requires less energy to remove. The second exception occurs between groups 5a and 6a. So if we go back to our graph, the second exception occurs here. So what's causing that second exception? Well, the difference between 5a and 6a is that 5a has 3 electrons in the 3 separate orbitals of p, according to Hund's rule. 6a has an extra electron that must be paired with one of the 3p electrons. This 2 electrons in the same orbital results in a greater electrostatic repulsion, therefore it's easier to remove. Remember that having a half-filled or filled sublevel is more stable. So our 6a, having that extra electron, it's going to be easier to remove that and create a half-filled situation than it is to take the half-filled and remove an electron. So which of the following atoms would have the larger first ionization energy, nitrogen or phosphorus? Nitrogen would require more energy to remove its valence electron because it's a smaller atom. So that valence electron is closer to the nucleus and is held strongly by the attractive forces. Which of the following atoms would have a smaller second ionization energy? Well, magnesium would have a smaller second ionization energy because sodium only has 1 valence electron. So the second electron being removed would be a core electron requiring greater energy. Electron affinity, or EA, is the negative of the energy change that occurs when the electron is accepted by an atom in a gaseous state to form an anion. The more positive the value of electron affinity, the greater the ability of the atom to gain the electron. So electron affinities are hard to measure because the anions of many elements are unstable. So like potassium negative, potassium doesn't want to be negative, so it's a very unstable anion. So it's hard to measure that. There's an increase in the tendency to accept electrons, so the values are more positive across the period. So as you go from left to right, electron affinity increases. Metals tend to have lower values than nonmetals, and halogens have the highest value. They want to gain the electron the most. The noble gases actually have a value of 0. So that's why on the graph here we have some zeros, and that's our noble gases. They don't want to gain electrons at all. Our fluorines, again, our halogens have the highest in each row.